left for tomorrow, we'll see. It depends on how fast we will go. So, let us go to the very basics, because I don't know how my praise to them. But maybe not all of us are so good, so let's go through the basics as well. So, when we say that G is a simple graph, it means that it consists of a set of vertices. In this particular case, we have the set of vertices A, B, C, D, and E. And it consists of edges between some of the vertices. Now, edges, because it's a simple graph, edges will not have orientation. So edge will connect two vertices and they're equal, they're symmetric. And there is no possibility for multiple edges, and also there are no loops. Loops would be an edge that connects a vertex to itself. They are helpful at some point, but in this setting we're just going to look at simple graphs at the moment. Most of the results are easily expandable to more general settings, but they're nicest in the setting of simple graphs. So in this particular case, we also have the set of edges. So AB, AC, BC. So this is a bow tie graph. It has two triangles and it can fit on your neck. So we will also most often denote the number of vertices as n, which is 5 in this case, and the number of edges will often be denoted by m. So we say that two vertices are adjacent if there is an edge between them, and we will also shortly write that u tilde v to denote that two vertices are adjacent, or actually the actual edge will be denoted by uv, that it belongs to the set of edges. Now the main culprit in this story is the adjacency matrix, which is indexed by the vertices, and usually so I have written the vertices here just to illustrate the matrix, but usually we don't write the vertices. And it is defined in a very simple way. Each entry of UV entry of the adjacency matrix is equal to 1 if two vertices are adjacent, and 0 otherwise. So over here we have the adjacency matrix that corresponds to the graph above. So we see that and I obviously made so C. What is written as C, it should be A, because apparently there is some reordering in this matrix. So let us work out what went wrong here. So this vertex that is adjacent to everybody else, this should be A, and over here, besides that, we have two edges. So we have an edge between actually B and A. So A and B are joined by an edge, and to each edge we actually have two entries equal to 1 in the adjacency matrix. So I mixed up A and C in this ordering here. Okay, great that we all saw it. So what is important for us is that the adjacency matrix is a real symmetric matrix, which means that we can start considering its eigenvalues and eigenvectors. Why do we go straight to eigenvalues and eigenvectors? Well, because we hope that some information about the graph will be contained there. Now, it's not all possible information, because we know for a very long time that there are many sets of graphs which are not isomorphic, so have different invariants. Some of the invariants are different, but they are isospectral, meaning that they have the same eigenvalues, and so the same eigenvalues, but usually not the same eigenspaces, otherwise it would be fully reconstructible. So the spectra, eigenvalues and eigenvectors are not all powerful, but still they bring us some information. So what is the basic that we build upon? It's the spectral theorem, which says that any real symmetric matrix has, if its dimensions are n times n, then it has n real eigenvalues counted with multiplicity, and eigenvectors can be chosen to form an orthonormal basis. So let us recall immediately what orthonormality means. It means that the length of each the eigenvector is equal to 1 norm, and it means that the product of any two eigenvectors, the scalar product, is equal to 0. So we will denote the adjacency eigenvalues mostly, almost all of the time by lambda 1. Lambda 1 is the largest, and order them down to lambda n is the smallest one, and we will drop the subscripts or drop the notation of G if it's necessary. When we have eigenvalues of different graphs, we will have to say that it is lambda 1 of G or lambda 1 of whatever other graph we have. The corresponding orthonormal eigenvectors will usually be denoted by x1, x2, up to xn, and that's what we are going to build upon. So the very first thing that we have from the spectral theorem is actually spectral decomposition. The way to express adjacency matrix in terms of eigenvalues and the eigenvectors. Now, not just a tiny little thing, we switched the transpose sign here. So on the previous slide, we were interested in scalar products of vectors. So we wrote xi transpose times xi in order to get 1, just a single number. But over here, we actually want to get a matrix. So we multiply a column vector. So over here, we multiply a column vector with its transpose, which is a row vector, and then we actually get products of all pairs of components of this eigenvector. They fit the corresponding entry, and then they build up the adjacency matrix. Now, how can we see that this is actually correct? Well, let's form the difference between the adjacency matrix and this expression that we wrote. The easiest thing that we can do is to multiply this matrix B, this difference, with each of the eigenvectors in turn. So what happens when we multiply? Over here we have adjacency times xk. Well, xk is eigenvector, so it translates to lambda k minus xk. And over here, xk multiplies each of these summands. Now, here is where we use orthonormality. So if I and k are different, then their scalar product is equal to 0, and then that summand vanishes. So out of all these summands, only the one where I is equal to k survives. So we have minus lambda k, xk transpose xk, and of course it remains to use also the fact that the eigenvector xk has norm 1, so this product is equal to 1, and then it goes down to lambda k xk minus lambda k xk, which is 0. So what happens is that B, matrix B, maps each basis vector of the whole space to 0, and that's possible only if matrix B itself is a 0 matrix. If it would have a single non-zero entry, then the previous, some basis vector would be mapped to something which is not 0. So we have the spectral decomposition that will be very helpful later, especially when we take powers of the adjacency matrix. Because of this orthogonality, when we raise the adjacency matrix to the, say, rth power, then the eigenvalue lambda I would be raised to rth power, and that would be the only difference. So we will have the same expression, except that over here it would be lambda I to the power of r. Orthonormality would take care of anything that we would get by usual exponentiation. Okay, in order to be able to express our first bounds, we also need to introduce some further notions. So the degree of a vertex is actually the number of vertices that are adjacent to that vertex. So these are neighbors of V. So over here we have the degree of this central vertex is equal to 4, as it is adjacent to everything else. And the degree of remaining vertices are equal to 2. So each of them is adjacent to the central vertex and to one additional vertex. The degree will usually be denoted by d of V, or deg of V, depending on the case. And we need to introduce some further notation for three special degrees. So the largest degree will be denoted by large capital delta sub G. We will often take away that subscript. The smallest degree is denoted by small delta, and then we also will often need the average degree, so the average of all degrees. But if we recount that the sum of all degrees is equal to twice the number of edges, so because each edge is actually counted once in the degree of one of its ends and once in the degree of the other of its ends, then we can see that actually each edge contributes to the sum of degrees of all vertices. So the sum of degrees of all vertices is 2m, so the average degree is just 2m over m. And that's what we will also very quickly see, that it is related to the largest eigenvalue. So what is our first bound? Very basic one, that the largest eigenvalue of adjacency matrix is bounded from above by the maximum degree. At the moment, we just prove the bound, and we will deal later with the case of equality, because in order to characterize equality, we need some further results. But we can see this bound already from the spectral decomposition. So what do we need to do it here? We know that for lambda 1 and x1, we have eigenvalue equation. And if we look at a particular row of this matrix equation, which corresponds to vertex V, on the right-hand side, we will see lambda 1 times the V component of the eigenvector x1. And on the left-hand side, we know that A contains ones if a vertex is adjacent. So in the V row V, it contains ones for the vertices that are adjacent to V. And it's 0 everywhere else. So in this product, only the terms, so we will have the sum of eigenvector components only for those vertices that are adjacent to our vertex V. So this is the eigenvalue equation when we consider at the level of a particular vertex. So what remains is to pick a particular vertex, the extremal one. So what is the extreme? We want that the eigenvector component of that vertex is maximal. And then we can see that the absolute value of this product, lambda 1 times x1 v, that's the absolute value of the sum. And of course, it is less than the sum of absolute values. But now, each of these absolute values, x1 u, absolute value, is less than or equal to x1, absolute value of x1 v. That's why we chose the maximum, v to be maximum. And then the number of such summands is actually equal to the degree of v. So it is less than or equal to degree of v times the eigenvector component of v. And when we look at the far left and far right, and when we divide by x1v, which we know it is not 0, why it is not 0? If the maximum value, the maximum absolute value would be 0, that means that all the components of the eigenvector would be 0, then it means that the whole eigenvector would be 0. But the first thing that we say about eigenvectors is that they are not 0. So we can freely divide by absolute value of x1v, and then we get that lambda 1 is actually bounded from above by the degree of v. We don't know how much, we don't know which vertex exactly is v, but we know that its degree is bounded by the maximum degree. And so lambda 1 is less than or equal to capital delta, and most often, say 99% of cases, the vertex v will actually have the maximum degree. So there will be equality here most often. So let us go to the next of our topics, which is Rayleigh quotient. Rayleigh quotient is the name that is given to this funny-looking ratio here. Over here we have quadratic form, x transpose times adjacency matrix times x, which actually corresponds, because adjacency matrix has only 0 and 1 entries, and entries 1 are present only when two vertices are adjacent. So this quadratic form will actually correspond to the product of components, of those components of the eigenvector, of the vector x, those components whose vertices are adjacent. So it will be the sum over all edges xu times xv. And down here we just have the length of the vector x to normalize it, and we claim that the largest eigenvalue of A is the maximum of all these ratios. And moreover, the maximum will be attained when x is an eigenvector that corresponds to lambda 1. Now, how do we get this? Well, we use the fact that the eigenvectors x1 to xn form an orthonormal basis, and therefore each vector x is expressible as a linear combination of the eigenvectors with some coefficients c1 up to cn. We also have the spectral decomposition, and then we can work out the product of adjacency matrix and the vector x. So adjacency matrix is just the sum of these products over all I going from 1 to n, and x is the sum of the linear combination of eigenvectors, where we put a different index, j, also going from 1 to n, so that we can combine the two sums into one sum in both indices, in index I and index j, both going from 1 to n. And of course, we just multiply the terms, so it's lambda I times cj and times this product, scalar product, this product of vectors. Now, of course, we're relying on orthonormality, so this last two terms will give us 0 whenever I and j are different. So out of this double sum, only the terms with I equal to j will survive, and in that case we know that xi transpose times xi is equal to 1, so that the actual product A of adjacency matrix and x will be representable in this form. And now we can work out the actual Rayleigh quotient. So once again, we use two different indices, sum of the linear combination that gives us x, indexed by j, and this linear combination that represents the product of A and x, divided by the product by the product of x with itself, but expressing these linear combinations. And now when we again combine these two sums, only the terms where when I is equal to j, only those survive. And of course, in such summands, we will have that xi transpose times xi is equal to 1. So this whole product of all will be just the sum of lambda I times ci squared, and below we will have the same situation but without lambda I. So it will be just the sum of ci squares. So we see that this ratio is actually a combination of eigenvalues, lambda 1 to lambda n, a convex combination of those eigenvalues, and since lambda 1 is largest, we will have that each of these summands is less than or equal to lambda 1 times ci squared. So it will, ci squares, the sum of ci squares will cancel out, and we will have that this Rayleigh quotient on the left is necessarily bounded from above by the largest eigenvalue, by lambda 1. What remains is to see why is the maximum attained only when x is an eigenvector. So if we know that x is an eigenvector, then A times x is equal to lambda 1 times x, and then this then we immediately, trivially saw that this Rayleigh quotient is equal to lambda 1. Now, if we know that, on the other hand, if we know that the Rayleigh quotient is equal to lambda 1, then since Rayleigh quotient is a convex combination of the eigenvalues, then we know that Ci must be 0 whenever lambda I is strictly less than lambda 1. So recall, in this case, we only assume that lambda 1 is greater than or equal to lambda 2, greater than or equal to lambda 3, so maybe lambda 1 will be equal to lambda 2 for some graphs. In particular, if graph has two components, two disconnected separate components, and each of them has lambda 1 equal lambda 1 for itself, then when we combine them, for the large graph, we will have equality lambda 1 equals to lambda 2. So, what we know is that Ci, the coefficient of, when we express x as a linear combination of eigenvectors, the coefficients are 0 for each eigenvector that corresponds to eigenvalues strictly less than lambda 1. But then it means that what remains is that x is a linear combination of eigenvectors that correspond to lambda 1, and as such, x must be an eigenvector for lambda 1 by itself. So that settles the case of equality in the Rayleigh quotient as well. So let's go back to summarize. Maximum of all these quotients, maximum of all these ratios is equal to lambda 1, or when we take any particular x, we know that lambda 1 will be larger than or equal to the ratio to the Rayleigh quotient for that particular x. And we can have equality only when x is an eigenvector for lambda 1. Over here, we're mostly interested in the spectral radius, which is why we don't use the other eigenvalues, but it is very, very easy and fully analogous to show that the smallest eigenvalue, lambda n, is actually equal to the minimum of all these Rayleigh quotients. And if you go further into linear algebra, you will be able to see that lambda 2 can also be expressed in terms of Rayleigh quotients if you only consider vectors x that are orthogonal to the eigenvector, to the eigenspace of lambda 1. So if you exclude those from consideration, then lambda 2 will be still the maximum of Rayleigh quotients, and so on. But for our case, just lambda 1 is enough. Okay, and let us see the first application of the Rayleigh quotient. So we have already seen that lambda 1 is smaller than or equal to the largest degree. This time we see that lambda 1 is greater than or equal to the average degree, and it's very straightforward using a particular vector. So we will use the all one vector j, so all components of j will be equal to 1, and then the Rayleigh quotient tells us that lambda 1 is greater than or equal to j transpose times a times j over j transpose j. Over here, the product of any two terms of any two components of j is equal to 1, but it goes over all the entries, so only the entries that correspond to adjacent vertices survive. And recall, we have 1 for each edge. Each edge in the graph gives us 2 symmetric entries equal to 1 in the adjacent symmetric. So actually, this product above is equal to twice the number of edges, and below we have just the number of vertices, and now that's the average degree. Still, to characterize the case of equality in both of these bounds, we need to know one more basic theorem, and that will be a very important one, Perron-Frobenius theorem, which will tell us further things about lambda 1 and x1, very nice things. But in order to be able to state it and prove it, we need a few more definitions from ordinary graph theory. So, a walk between some two vertices u and v in a simple graph is simply a sequence of vertices. So we will start with the vertex u, and then we will list the vertices until we come to vertex v at the end. Now, what is important? Well, we want to walk across the graph, which means that any two any two consecutive vertices in our list should be adjacent. So W0, W1 should be an edge of G, W1, W2 should be an edge, and so on. And of course, the length of the walk is equal to the number of edges in it. And certainly, if there is a walk between two vertices, then that walk is if there is a walk, then there are many walks between two vertices. So over here we have examples of 3 different walks between vertices A and C with this with this ordering of vertices. So over here we can go from A up to B, then to C, up to D, and down to E. Or maybe we can take a shortcut and go from A straight to C, then follow to D and back down to E. Or maybe we can take just the shortest walk if we don't want to lose our energy on walking, or if we don't want to enjoy our walk, we can just go straight from A to C, C to A, and then these 3 walks have different lengths. Now, we say for a graph that it is connected if there exists a walk between any 2 vertices of G. So not just some 2 particular, but there should be walk between any 2 of them, and this graph this bow-tie graph is an example of a connected one, and over here we have an example of a disconnected graph, which is not connected because there is no way to jump from one quadrangle to the other one. So all our walks will be limited to just one of these cycles. Now, these maximum connected subgraphs are called components. So this graph has 2 components, and what our Perron-Frobenius theorem wants to work with are connected graphs. So what does it say? It says that if a graph is connected, then lambda 1 is a simple eigenvalue. So it must, lambda 1 will be strictly larger than lambda 2 and all the other eigenvalues. And moreover, it says that lambda 1 has a positive eigenvector. Positive here means that all the components are strictly larger than 0. So all of them are positive. So what we need to know first is that, so I'll recall for a moment, the sum of all eigenvalues is equal to the trace of a matrix, and since we don't have loops in our graph, so no edge connects a vertex to itself, we only have zeros on the diagonal, so the trace will be 0. So if the sum of all eigenvalues is 0 and lambda 1 is the largest one, then it itself must be a non-negative one. So that will be needed later at the bottom over here. So where do we go next? Well, we will take an arbitrary eigenvector of lambda 1, x1. And what we will show is actually that out of x1, you can create one more eigenvector by taking absolute values of its components. So we will denote it by absolute of x1. So its components will be the absolute values of x1 for each particular vertex. At the end, actually, we want to show that x1 will be equal to the absolute value of x1. So that will be just a multiple of the same vector. But at the moment, it looks like we're creating a new eigenvector. So let's see what happens with this absolute of x1. We need to multiply it. In order to be able to use the Rayleigh quotient, we need to create the product, so the upper term in the ratio, the product of x1, absolute, transpose, adjacency matrix, and absolute of x1, which translates to the sum of the products of absolute values of components of x1 over all vertices, over all adjacent vertices. Now, that's the sum of absolute values, and of course it is greater than or equal to the absolute value of the sum. But if we just take the sum without absolute values, then we actually have the product x1 transpose A and x1 for x1 itself. So this part here is let's go to the next line. This part here, a times x1 is just lambda 1 times x1. And then we can just recall this scalar product is just the sum over all vertices u of the squares of components times lambda 1. And since lambda 1 is greater than or equal to 0, we can remove this absolute value. And actually, we can remove the absolute value from the outside the sum and put it inside next to these components. So what we get is lambda 1 times x1 absolute transpose times x1. So where we started is the upper term for the Rayleigh quotient, and we got along the way that it is larger than or equal to lambda 1 times the lower term. So actually, it means that the Rayleigh quotient for this vector is greater than or equal to lambda 1. And we already saw from the Rayleigh quotient that lambda 1 is greater than or equal to any Rayleigh quotient. So over here we must have an equality. And then it means that the absolute of x1 is indeed an eigenvector. So that's the first step. Our next step is to show that this eigenvector is nowhere zero, so it does not have any zero entry when the graph is connected. Now, this connectivity is where we use the fact that we have a walk from a particular vertex to all the other vertices. So what will happen is that if x1u is equal to 0 for some vertex, we will actually obtain that it must be equal to 0 for all the vertices. So this equality to 0 will spread around, spread from this vertex u to all other. How do we see it? Well, we know that the absolute of x1 is an eigenvector, so eigenvalue equation holds for it. Lambda 1 times the absolute of x1u is equal to the sum of absolute values of all the neighboring components. And now, since this is 0, and these are absolute values, it turns out that all these components must also be equal 0 for all the neighbors of u. Now we apply the same argument again for each neighbor of v. So for each neighbor v of u, so we will obtain then that its neighbors have 0 component of x1, and then we repeat the argument for the neighbors, and then we build. So we build a larger neighborhood of u where the eigenvector components are all equal to 0. Now, since G is connected, these neighborhoods will eventually spread over the whole graph G, and we will have that the whole eigenvector is equal to 0 over all graph G. But this is, of course, contradiction, as eigenvector must be non-zero. So what we have here is that the principal eigenvector x1 will, for a connected graph, will never have a 0 component. So in order, that will help us later. So what we know so far, that the absolute of x1 is a positive eigenvector for lambda 1. Now, we started with x1, which is ordinary eigenvector for lambda 1. We create the absolute of x1 and show that it is a positive eigenvector. But we still have to show that lambda 1 is simple, which means that there will be no other eigenvectors but multiples of the absolute of x1. So in order to know that, we need to show that x1 has the same sign everywhere. For all the vertices, it will either be all positive or it will be all negative. So we go back to the equality over here, because we know that the absolute of x1 is an eigenvector. That means that we have equality here from 2 pages back. So this means that the sum of absolute values is equal to absolute value of the sum, which means that all the products x1u times x1v for adjacent vertices, they all have the same sign. Now, they might all have the positive sign, or maybe they all have the negative sign. We don't know that up front. So, for a fixed V from the set +1 or -1, we have that the product of these components is equal, not V, W. We have that the product of these components is W times the product of their absolute values, or, well, we can also put it in a normalized form that x1, the ratio of a component and its absolute value is equal to W times the ratio of the component of its neighbor divided by the absolute value. Now, when we just divide this equality with the product of absolute values, we will actually have that both of these, x1u over the absolute value and x1v over the absolute value, they will both appear on the left. But we use the fact that this ratio is equal to +1 or -1, so it is equal to its inverse, reciprocal value. So it means that we can move it from the left to the right in the same form, and we can write this equality. So this happens whenever u and v are adjacent. So let us look now at the eigenvalue equation at vertex v. So lambda1 times x1v is equal to the sum of components of all neighboring vertices. Now we use this relation to express the component x1u in this funny form. So w, it looks more complicated, right? But what is important here is that we have the sum of absolute values of components of all the vertices that are adjacent to v. Now, since the absolute of x1 is an eigenvector, this sum will be just equal to lambda1 times the absolute of x1v. And then it will cancel out, and we will have lambda1 times w times x1v. And when we compare it to lambda1 times x1v on the left, and we know that now w must be 1. So actually, all the products of of components of neighboring vertices are positive. So not positive or negative, they must all be positive. And then it means that either both components are positive or both components are negative. But then again, our graph is connected, so we can use, and over here we have the claim which relates to neighboring vertices. So we can start from an arbitrary vertex u, and we conclude that all its neighbors have the same sign as x1u. And then we can go to the neighbors of v, they will have the same sign again, and to their neighbors, and so on. So we can conclude that actually the whole vector xv has all components in x1 actually have the same sign as this one particular component. In other words, either we will have that x1 is equal to the absolute of x1, or maybe x1 will be minus of the negative of the absolute of x1. So actually we will not have independent eigenvector, but we will have that they are both expressible one in terms of the other linearly. And one more thing. x1 was an arbitrary eigenvector for lambda1. So for arbitrary eigenvector this holds, and we know that each eigenvector has the same sign everywhere. So it remains one more step is to show that lambda1 is actually a simple eigenvalue, but now that we know that each eigenvector has the same sign everywhere, it is very simple, because if lambda is not a simple eigenvalue, then we can choose two orthogonal eigenvectors, x1 and y1, and each of them is either all positive or all negative. In any way, their scalar product will be the each of the sum and the scalar product will have the same sign. And what we get is actually that, and not only the same sign, each of the terms here is non-zero. So actually this colored product will be either positive or negative. It can never be equal to zero. And for any two orthogonal eigenvectors, that's what we would like. So this is a contradiction, which means that we cannot have two independent eigenvectors for lambda 1. So if a graph is connected, lambda 1 must be a simple eigenvalue. Moreover, this gives us an easy way to recognize the largest eigenvalue, because if we are able to create, construct, to find a positive eigenvector of adjacency matrix, then it must necessarily